in the last class I have discussed one example. Let me continue with that example. We have a random sample from normal 0 sigma square distribution, and we are considering the estimation of sigma in place of sigma square. So, what I showed in the last class is that the Rao-Kramer lower bound for estimation of sigma is sigma square by 2 n. Now, I will propose two estimators for the estimation of sigma, and we will consider their variances, and then we will see whether the FRC lower bound for them is attained or not. In fact, we have seen that for sigma square it is attained. Now, sigma is not a linear function of sigma square, therefore, this bound may not be will not be attained. However, we will consider two examples. So, let me take the first example. Consider an estimator of the form say V alpha is equal to alpha into sigma modulus of x I is equal to 1 to n. Now, if you consider say expectation of modulus x I, that is equal to integral from minus infinity to infinity modulus x 1 by sigma root 2 pi e to the power minus x square by 2 sigma square dx. Now, this is an even function. So, this will become 2 times 0 to infinity x 1 by sigma root 2 pi e to the power minus x square by 2 sigma square. Now, this can be easily evaluated, because derivative of e to the power minus x square by 2 sigma square is e to the power minus x square by 2 sigma square into x by sigma square. So, if you evaluate this integral, this turns out to be simply 2 sigma divided by root 2 pi. So, if we consider expectation of V alpha, that will be equal to twice n sigma by root 2 pi alpha. Now, if we want that V alpha be an unbiased estimator of sigma, then we substitute this equal to sigma, that gives the value of alpha is equal to 1 by n root pi by 2. So, what we are getting is that, let me call this estimator as T 1 by substituting alpha is equal to this value, that is 1 by n root pi by 2 sigma modulus of x I. This is unbiased estimator of sigma. Let us look at the variance of T 1. So, what is variance of T 1? Variance of T 1 will become pi by 2 n square into n times variance of modulus x I. Now, this becomes pi by 2 n. Now, variance of x I is expectation modulus x I square, that is expectation of x I square, and minus expectation of modulus x I whole square. Now, since we have considered here the normal 0 sigma square, so expectation of x I square is nothing but the variance, that is sigma square. So, this value is equal to sigma square, and expectation of modulus x I we have just now calculated. So, if we substitute the square of that, I get 2 sigma square by pi. So, this can be written as pi minus 2 by. So, what I am doing is I will adjust this term pi minus 2 by pi, and then 2 n is there. So, 2 n pi sigma square. Now, this can be shown that this is bigger than sigma square by 2 n. Similarly, so we can say that T 1 does not achieve FRC lower bound. And if you look at the estimator here, see the variance is certain term divided by n. So, as n tends to infinity, this goes to 0 and it is unbiased. So, this is unbiased, T 1 is unbiased as well as consistent. Let me define another estimator here. Let me call it say W beta, that is equal to beta times sigma x I square to the power half. Now, if we want to evaluate the expectation of this, we can consider if x i's follow normal 0 sigma square, then x I by sigma that will follow normal 0 1. So, the sum of squares of standard normal variables when they are independent is a chi-square random variable. So, we get here that u is equal to sigma x I square by sigma square, this follows chi-square distribution on n degrees of freedom. Now, if I have a chi-square, then expectation of u will become root 2 gamma n plus 1 by 2 by gamma n by 2. Therefore, expectation of W beta that turns out to be beta times root 2 and here we will get gamma n plus 1 by 2 by gamma n by 2 sigma. Once again, if I want this to be unbiased, then I equate it to sigma, that means beta should be equal to gamma n by 2 divided by root 2 gamma n plus 1 by 2. So, T 2 is equal to gamma n by 2 by root 2 gamma n plus 1 by 2 sigma x I square to the power half. This is also an unbiased estimator of sigma. Let us look at what is variance of T 2. Variance of T 2 is half gamma n by 2 divided by gamma n plus 1 by 2 whole square into variance of sigma x I square to the power half. Now, variance of sigma x I square to the power half that is expectation of sigma x I square minus expectation of sigma x I square whole square. Sigma x I square to the power half whole square. Now, these terms we have already calculated. So, that becomes, let me call it this some constant n minus twice gamma n plus 1 by 2 by gamma n by 2 whole square sigma square. That we can write after simplification as n by 2 gamma n by 2 divided by gamma n plus 1 by 2 whole square minus 1 sigma square. It can be shown that variance of T 2 is greater than sigma square by 2 n and variance of T 2 is less than variance of T 1. In fact, one can show that this also goes to 0 as n tends to infinity. So, T 2 is more efficient than T 1. Now, we have discussed in detail one lower bound for the variance of an unbiased estimator, and this lower bound takes into account one derivative of the log of the density function. Now, naturally there is a question whether one can further sharpen it or whether we can extend it to multi-parameter case or whether if the regularity conditions are not satisfied, then this will be true or not. Fortunately, in all the directions the extensions of this result have been done. So, let me discuss this here. The first of this is known as Bhattacharya bound. So, this was proposed by A. Bhattacharya in 1946. Now, in the Fréchet-Rao-Kramer lower bound, we had considered first order derivative, and of course, second order derivatives condition was assumed. However, in the Bhattacharya bound, higher order derivatives are used, and therefore, we have to make the assumptions accordingly. So, once again, as in the Rao-Kramer lower bound, let us consider the regularity conditions in the same way. So, we have a random sample, let x 1, x 2, x n be a random sample from a population. Now, again it may have a probability density function or probability mass function, say f x theta, theta belonging to omega, where omega is an interval on the real line. Let us define S I to be ith order derivative of the joint distribution divided by the joint distribution. You compare it with the Rao-Kramer lower bound. In the Rao-Kramer lower bound, we had first order derivative here. Now, I am defining higher order derivatives also, because in the first order derivative it will become del by del theta of the density divided by the density, that is del log of that, but here it is higher order here. So, I is equal to 1, 2 and so on. Suppose I am assuming up to order k. Let the following conditions hold. So, we have already assumed that the parameter space is an interval in the real line. Let us consider open interval. Let us assume that the ith order derivative of the density exists for all theta for almost all x. By almost all x means that the set where this is not existing will have probability 0. The density function, once again I am writing this is a multifold integral, and this is a generalized integral, that means it takes care of the discrete case also. In that case, this will be summation. This can be differentiated under the integral sign at least I times. Let us define S I as this term, then we assume that S 1, S 2, S k are linearly independent. By linearly independent means that none of them can be expressed as function as linear combination of the others, and this manifold integral this also can be differentiated under the integral sign I times I is equal to 1 to k for any integrable. That means, this should exist for any integrable function delta. let us define say lambda I j to be the covariance between S I S j for I j equal to 1 to k. So, if I is not equal to j, then this will be covariance, and lambda I is variance of S I for I is equal to 1 to k, and let lambda be the matrix of lambda I j's for I j equal to 1 to k. Let us denote by lambda say R s, denote the R sth term of the matrix lambda inverse. Then, and also we can write here let us write eta I vector to be covariance of T S I, that is equal to d g d I g by d theta I. Now, what is T here? T is an unbiased estimator of g theta. So, let us look at the problem here once again. We have a probability mass function or probability density function f x theta. We have a random sample x 1, x 2, x n from here. The parameter space omega is it has an open interval on the real line. We define the derivatives of the joint density divided by the density as S I, and then we have certain conditions, because for the existence of this we should have the derivatives existing. Then we should also have, and this should be true for I is equal to 1 to k. Then this integral we should be able to differentiate under the integral sign. Then the terms s 1, s 2, s k should be linearly independent, and for any integrable function delta x we should be able to once again differentiate this integral delta x product of f x j theta d mu x. Further we define certain quantities. Let us call this lambda to be the variance covariance matrix of s 1, s 2, s k, and we consider lambda inverse, and the terms of lambda inverse we denote by lambda R s. I am defining some additional things. Let T be an unbiased estimator of g theta. So, I am considering in general estimation problem for any parametric function, say g theta. So, T is an unbiased estimator. Let us consider the derivative of expectation T x. So, if I consider the ith derivative, it will give me expectation of T s I. Since expectation of S I is 0, this becomes covariance, and I denote it by eta I for I is equal to 1 to k, and let us denote eta vector to be eta 1, eta 2, eta k. Then Bhattacharya's bound is that variance of theta, variance T is greater than or equal to eta prime lambda inverse eta, which is nothing but lambda R s d r g by d theta r d r d s g by d theta s. You can see that if I had considered k equal to 1, then this will reduce to the FRC lower bound. For k equal to 1, this will reduce to FRC lower bound. Let us look at the proof of this. So, expectation of T x is equal to g theta, which we can write as integral T x, the joint distribution of x 1, x 2, x n d mu x is equal to g theta. So, these statements are true for all theta. Now, this relationship we differentiate, let me call it 1. Differentiating 1 with respect to theta I times. So, I will get integral T x del I by del theta I product f of x j theta j is equal to 1 to n d mu x is equal to, on the right hand side we had g. So, d I g by d theta I. Now, this term we can consider as T x del I by del theta I this. I divide it by product of f x j theta. If I divide by this term, this becomes nothing but S I, and then I can express it as S I into product f x j theta, j is equal to 1 to n d mu x is equal to d I g by d theta I. This is nothing but expectation of t into S I. Now, since we are assuming that the density can be differentiated under the integral sign, therefore, if we differentiate this relationship, this is equal to 1. So, if I differentiate this, I will get expectation of S 1 is equal to 0. Similarly, if I differentiate it twice and again divide by that, I will get expectation of S 2 is equal to 0. So, what we are getting now, expectation of S I is 0 for I is equal to 1 to k. So, this relation is then equivalent to covariance between T and S I is equal to d I g by d theta I. So, now let us consider the multiple correlation coefficient between T and S 1, S 2, S k, that is equal to, let me use the notation say capital R square, that is equal to eta prime lambda inverse eta divided by variance of T, because lambda was the dispersion matrix of S, that is S is equal to S 1, S 2, S k. So, if I apply the formula for the multiple correlation coefficient, I get eta prime inverse lambda inverse eta divided by variance of T. Now, this is less than or equal to 1, because multiple correlation coefficient lies between 0 and 1. Let me write R, not R square. So, I get eta prime lambda inverse eta less than or equal to variance of T. Now, this is nothing but the Bhattacharya's bound. Variance theta t is greater than or equal to, let me call it star, and if I expand these terms, then I get this. So, you notice here that in the Frechet-Rao-Kramer lower bound, we had used that the correlation is less than or equal to 1, and here we are using, in fact, correlation square is less than or equal to 1. Here we are using multiple correlation square is less than or equal to 1. Let me explain through an example here. We consider our example of the geometric distribution, that is p theta x is equal to x is equal to theta into 1 minus theta to the power x for x is equal to 0, 1, 2 and so on. In fact, for this problem we have already shown that an unbiased estimator for theta is t given by that t 0 is 1 and t k is equal to 0 for k equal to 1, 2 and so on. In fact, this is the only unbiased estimator, unique unbiased estimator. And we have already seen that variance of t is theta into 1 minus theta, and the FRC lower bound was equal to theta square into 1 minus theta. Now, let us apply Bhattacharya's bound here. So, let us calculate here f x theta is equal to theta into 1 minus theta to the power x. So, del f x theta by del theta, that is equal to 1 minus theta to the power x plus x into 1 minus theta to the power x minus 1 with a minus sign. So, S 1 is del f x theta by del theta divided by f x theta, that will be equal to 1 by theta minus x by 1 minus theta to the power x minus 1 divided by this term. So, we will get it as theta into 1 minus theta to the power x. So, I am sorry, this is theta here. So, I will get here x by 1 minus theta. Similarly, if we consider say second derivative here, del 2 f by del theta 2, we get here x into 1 minus theta to the power x minus 1 minus x into 1 minus theta to the power x minus 1 minus plus x into x minus 1 theta into 1 minus theta to the power x minus 2. These two terms can be combined. So, S 2, that is del 2 f by del theta 2 by f x theta, that becomes minus 2 x by theta into 1 minus theta plus x into x minus 1 minus theta square. Now, for this geometric distribution, if I want to calculate variance covariance matrix of S 1, then I need various expectations. So, let us see. In fact, I will need expectation of x square, and if here I will need expectation x square, and expectation x cube and expectation x to the power 4 also. So, let us see for this geometric distribution, you will have expectation x is equal to 1 minus theta by theta, expectation of x square, that is equal to 1 minus theta plus 1 minus theta square divided by theta square, expectation of x cube is equal to 1 minus theta plus 4 into 1 minus theta square plus 1 minus theta cube divided by theta cube, expectation of x to the power 4, that is equal to 1 minus theta plus 11 1 minus theta square plus 11 1 minus theta cube plus 1 minus theta to the power 4 divided by theta to the power 4. So, if we use these expectations, we can easily write down expectation of S square, that is variance of S 1 as 1 by theta square into 1 minus theta, expectation of S 2 square, that is variance of S 2, that is equal to 4 into 2 minus theta divided by theta to the power 4 into 1 minus theta square. We also need the covariance between S 1 S 2, that is expectation of S 1 S 2, because expectation S 1 and expectation S 2 are 0. This is equal to minus 2 divided by theta cube into 1 minus theta. Therefore, the variance covariance matrix of S is equal to S 1. So, here we are going only up to second stage, that is lambda 1 by theta square into 1 minus theta minus 2 by theta cube into 1 minus theta and 4 into 2 minus theta divided by theta to the power 4 into 1 minus theta square. Now, the inverse of this can be written easily. If we look at the determinant of this, it is 4 divided by theta to the power 6 into 1 minus theta cube, and the inverse is then simply obtained as 2 minus theta square into 1 minus theta cube 1 minus theta square by 2 theta cube into 1 minus theta square by 2 theta to the power 4 into 1 minus theta square by 4. We also look at what is eta. Eta 1 is d g by d theta, that is 1. Eta 2 will become d 2 g by d theta 2, that is equal to 0. So, your eta vector is 1 0. So, Bhattacharya's bound for estimating theta unbiasedly is, I will call it BLB, Bhattacharya lower bound, or say BHLB, that is equal to eta prime lambda inverse eta. Since eta is 1 0, so you will get actually the first term, that is theta square into 1 minus theta into 2 minus theta. What was FRC lower bound here? That was theta square into 1 minus theta, that is expectation of 1 by S 1 square here. And what is variance of t? Variance of the unbiased estimator t, that was theta into 1 minus theta. So, it is greater than Bhattacharya lower bound, and that is greater than FRC lower bound for theta lying between 0 and 1. Now, what you observe here is that although this unique unbiased estimator t, so therefore, it is the best unbiased estimator, it does not achieve the Bhattacharya lower bound, but Bhattacharya lower bound is sharper than the FRC lower bound. So, in that sense, this is an improvement over the FRC lower bound, although we are making an assumption about the differentiation of the density function a higher number of times. So, let me give a few comments here about Bhattacharya's bound. Equality in Bhattacharya's bound is attained if and only if T is linearly related with S1, S2, Sk. Now, why is this? Because actually we are using that the multiple correlation coefficient is less than or equal to 1. So, multiple correlation coefficient is equal to 1 provided the dependent variable and the independent variables are completely linearly related. So, that is the condition here, because we are considering the multiple correlation between T and S here. So, they must be linearly related with probability 1. Then we have observed that Bhattacharya's bound is sharper than the Rao-Kramer lower bound. Why? Because the Bhattacharya bound is using multiple correlation coefficient between T and S1, S2, Sk, and Fréchet-Rao-Kramer lower bound has only the correlation between T and S1. So, certainly this multiple correlation coefficient will be higher than that. So, we can say in general that Bhattacharya's bound is sharper than FRC lower bound, since multiple correlation coefficient between T and S1, S2, Sk is larger than the correlation between T and S1. Another thing that you observe, here I have considered derivative up to order k. Suppose I consider up to order k plus 1. In that case, the inequality will be dependent upon the multiple correlation between T and S1, S2, Sk plus 1. Now, if you increase the number of variables, the multiple correlation coefficient increases. That means, the Bhattacharya bounds gets sharper and sharper as k increases. So, we can say that Bhattacharya's bound gets sharper as k increases. This is because the multiple correlation coefficient between T and S1, S2, Sk plus 1 is larger than the multiple correlation coefficient between T and S1, S2, Sk. Now, you can see the historical development. The Fréchet-Rao-Kramer lower bound was obtained in 1943, 44, 45, and it was dependent upon one derivative or first order derivative. However, this Bhattacharya's bound, which was developed immediately after that, it is sharper, it uses higher order derivatives. Now, theoretically speaking, this should be used more often. However, it is not very popular, or you can say not frequently used. The main reason is that the calculations become very complicated if we use higher order derivatives. I have shown the example of second order here. So, if we are using the second order, we are actually making use of the expectation x to the power 4, that is the fourth order moment. Now, if you consider distributions like normal distribution etcetera, where already x square comes. So, if you consider the second order derivative, you will get power 4. Now, if you take the variance of that, you will get expectation of x to the power 8 kind of term, and therefore, if I go to third order or fourth order, the number of terms will be formidable, and therefore, even though you get sharpness, the method of Bhattacharyya bound has not been used much for finding out the lower bounds for the variance of unbiased estimators. I will just consider one example here. Let us take, say, normal distribution, and I will show that how the calculations become complicated, although Bhattacharya's bound is sharper, the use of it is limited due to complications in evaluation of the bound, which involves higher order moments quite frequently. Let me give an example of this. Say x 1, x 2, x n follow normal mu sigma square. So, here the density function is 1 by sigma root 2 pi e to the power minus x minus mu square by 2 sigma square we are considering sigma here. So, the derivative of this with respect to sigma del f over del sigma square. So, that will involve derivative of this, that will be e to the power minus x minus mu whole square by 2 sigma square and of course, 1 by sigma root 2 pi, and derivative of this term, that is x minus mu whole square by 2 sigma to the power 4. Now, we consider derivative of this. Now, this term we will consider as sigma square to the power half. So, the derivative of that will become minus 1 by 2 sigma square to the power 3 by 2, and then you have root 2 pi e to the power minus x minus mu square by 2 sigma square. Now, you can see this is S 1 term itself will be equal to x minus mu square by 2 sigma to the power 4 minus 1 by 2 sigma cube root 2 pi. Now, this term of course, will cancel out. So, you will get sigma square here, that is 1 by 2 sigma square x minus mu by sigma whole square minus 1. Now, if I want to calculate expectation of S 1 square, that will involve fourth order moment here. Of course, we may take help of the calculation that x minus mu by sigma, that follows normal 0 1. So, x minus mu by sigma whole square, let me call it w, that follows chi square on 1 degree of freedom. So, expectation of S 1 square can be written as 1 by 4 sigma to the power 4 expectation of w minus 1 whole square. So, if w is chi square 1, expectation of w is 1. So, this is variance term. So, that becomes 2 by 4 sigma to the power 4, that is 1 by 2 sigma to the power 4. Now, if we calculate S 2, S 2 will involve the second derivative here. So, if we consider the second derivative of this, then this density multiplied by this term you have to differentiate, and then differentiate the density also. So, you will get the terms like this del 2 f by del sigma square that is equal to 1 by 2 sigma to the power 4 minus x minus mu square by sigma to the power 6 into the density plus 1 by 2 sigma square x minus mu by sigma whole square minus 1 whole square into the density. So, your S 2 then turns out to be, we can write using this W term as follows: 1 by 4 sigma to the power 4 W square minus 6 W plus 3. Naturally, you can see that expectation of S 2 square will involve expectation of W to the power 4, and these terms you can see here. Expectation of W is 1, expectation of W square is 3, expectation of W cube that turns out to be 45 by 4, expectation of W to the power 4 turns out to be 105 by 2. So, you can calculate expectation of S 2 square as 1 by 16 sigma to the power 8, expectation of W square minus 6 W plus 3 whole square, which is 33 by 32 sigma to the power 8. So, you can see here the terms become complicated increasingly as we increase the order of derivatives in the Bhattacharya's bound. Here we have considered only second order. If we take third order and so on, it will be very cumbersome calculations. So, therefore, the use of Bhattacharya bounds is restricted. Now, I mentioned about two other things. One is the case of multi-parameter situation, what happens to the lower bounds in that case, and another is that what if the lower bounds are not there, sorry, if the regularity conditions are not satisfied, then what happens to the lower bounds. So, we consider the case when the regularity conditions may not be satisfied. So, we have the so called Chapman-Robbins and Kiefer inequality or lower bound for variance of an unbiased estimator. So, this is developed by D.G. Chapman-Robbins and Kiefer. So, let x have the probability density function or probability mass function, f x, I am already writing for sample here, where theta is belonging to omega. Let t be an unbiased estimator of g theta, and define a term like a phi theta. This is defined to be variance under the true distribution f x theta of f x phi divided by f x theta. That means, I am considering the joint distribution at the parameter point phi and the joint distribution at the point theta. Let us consider the ratio, and the variance of this is considered when the true distribution is f x theta. Obviously, when we write this ratio, we should have certain conditions. For example, I should not have the case when f x theta is 0 and f x phi is non-zero, because then this will give me an infinite term. That means, the set of values for which the density function f x phi is positive should be a subset of the set of points for which f x theta is positive. So, we should say here phi not equal to theta and the set x such that f x phi is positive is a subset of the set such that f x theta is positive. Now, then CRK, that is Chapman-Robbins Kiefer inequality, states that variance of t is greater than or equal to supremum of g phi minus g theta whole square divided by a phi theta. Now, the supremum is considered over all phi belonging to omega. Let me call this condition as star, where the supremum is taken over all phi for which the condition star holds. So, this Chapman-Robbins Kiefer inequality, this gives the lower bound for the variance of an unbiased estimator of a parametric function g theta, but we have not placed any condition on the density function, like in the case of Rao-Kramer or Bhattacharya's bound. We have placed conditions on the existence of the derivatives, of the integrals, etcetera. Here there is no such condition. The proof of this we will be considering in the following lecture, and you will again see that the proof is dependent upon the variance covariance inequality, or you can say Cauchy-Schwarz inequality, that is the correlation coefficient is less than or equal to 1. So, in the next lecture we will be proving this CRK inequality.